final speaker this morning is Paul Billant, Polytechnique.
So I am going to talk about the zigzag instability of vortex area in a stratified and rotating fluid. So this work has been done together with PhD student Axel Deloncle and Jean-Marc Chomaz. So the motivation for this work is to understand the formation of thin horizontal. Do you hear? To understand the formation of horizontal layer in stratified flows. So here is an example taken from an experiment where a rake of vertical bar were moved in a stably stratified fluid, and here we see a vertical cross section in the flow, and you see several horizontal layers. Here's another example taken from direct numerical simulation of decaying stratified turbulence, where again we see that the structures have a pancake shape. And this is a vertical cross-section still in numerical simulation, but of forced stratified turbulence. So we see the density perturbation in this vertical cross-section, and here we can see that we can see layers with elongated structure. So the horizontal length scale is much larger than the typical vertical length scale. And so the flow is strongly anisotropic. So the zigzag instability is one possible mechanism to explain the formation of such layers. So we have observed this instability on a pair of counter-rotating vortices, so with the stratification along their axis. And here you see the two vortices. So here they are coming towards you, and here this is a side view. So at the beginning they were uniform along the vertical. Now we see sinusoidal deformations. So these deformations evolve into zigzags now, and you will see that later. Now we start to have well-defined layers, and so the amplitude of the instability grows without to very large value. And so this instability can explain the spontaneous formation of layers in stably stratified flow. And this instability occurs only when the stratification is strong, when the fluid number is typically lower than unity. And one important property of this instability is that the typical wavelength scale like so the horizontal fluid number times b, the separation distance between the two vortices. And so this scaling implies that when the stratification increases, the wavelength decreases, and this implies that the vertical fluid number, so the fluid number based on the vertical scale of the flow, is of order unity and not small as assumed previously. So we have also observed a similar type of instability on the co-rotating vortices, so again in a strongly stratified fluid. So in this case, we see again a side view, and we see the two vortices which are rotating one around the other. So at the beginning, they are again vertical. And now we start to see sinusoidal deformation. And we see that this deformation accelerates the merging at some points and delay it at some other points. But finally, the vortex merging occurs all over the vertical. And also, we have also a look at the effect of planetary rotation in the case of two co-rotating vortices, and so by numerical stability analysis. And we have shown that this instability occurs when the fluid is strongly stratified, independently of the Rossby number, so whatever the Rossby number. And in fact, this instability is the same as the tall column instability observed by David Duetschel and Torre Juarez in quasi-geostrophic fluids. So here we see the case of two co-rotating vortices, and we see that these vortices are bent and that merge in a similar way as in the stratified fluid case. So now the question: this instability seems promising to explain the layers observed in stratified turbulence, but stratified turbulence is much more complex than two simple vortices. And so the question is this instability generic? And is it, shall we observe it when in many flow? And so to answer this question, I am going to present you a general theory of the zigzag instability in a stratified and rotating fluid. And we are going to look at the stability of vortex array, like the von Karman street. And so in the theory, we assume several hypotheses. So the first one is that we consider vortices which are well separated. So the distance between the vortices is large compared to the vortex radius. We also assume an unviscid fluid. And we assume that these vortices are perturbed by bending deformation, so like a solid body like that. And the wavelength of the deformation is also assumed to be large. And in fact, this hypothesis corresponds exactly to the hypothesis of vortex filament methods in homogeneous fluid. But here we consider a stratified and rotating fluid, so the fluid number and the Rossby number will be assumed to be arbitrary. And so the circulation of the vortices are not conserved. And so we cannot use vortex filament methods. And so what we have done instead is to do an asymptotic expansion of this form. So with the two small parameters of the problem, so R over B, the ratio between the vortex radius and the separation distance, and R over lambda, the wavelength of the deformation. And so at leading order, we consider, so the leading order perturbation consists in two-dimensional displacement of the vortices as if they were alone. And at the next order, we consider the strain effect, so the vortex, the interaction between all the vortices, and we consider also the leading three-dimensional effects. And when we insert this expansion in the Euler equation under the Boussiness approximation, what we obtain at the end is this equation. This is the equation for which governs the displacement perturbation of this vortex. So we assume that the vortex is bent sinusoidally, and so with a wave number k, and delta x1 and delta y1 is the amplitude of this displacement. And so this is the governing equation for this displacement. And so what is striking here is that these equations are in fact similar to those you obtain when you use vortex filament in homogeneous fluid. But we are going to see that there are important differences and when the fluid is stratified and rotating. So in this equation, there are three different physical effects. So, and I am going to present you them now. So this is the first one is a self-induction effect, which is described by these terms, and this is the effect of the vortex on itself. So when the vortex is bent like that, the bending deformation starts to rotate at angular velocity omega. And so here I recall you the self-induction in homogeneous fluid. So this is the self-induction for a small wave number. This has been obtained by a match asymptotic expansion. And so here you have the self-induction as a function of the wave number. And what is striking here is that the self-induction is always negative. So this means that the bending deformation rotates in the opposite direction to the basic rotation of the vortex. And so this can be also obtained from the Biot-Savart law. Now, in a stratified and rotating fluid, this is the equivalent formula, and for small wave number, it has been obtained also with a match asymptotic expansion. So now it depends on the fluid number and the Rossby number. And here is, for example, the self-induction for a fluid number equal to 0.9 and with no planetary rotation for infinite Rossby number. And now what is striking is that the self-induction is always positive. So this means that in this case, the bending deformation rotates in the same direction as the vortex. And in fact, this result is very general. we can show from this formula that as soon as the Froude number is lower than 1, the self-induction is always positive, independently of the Rossby number and the vortex profile. So when the Froude number is increased above 1, in fact, this is for 1.1, for example, in fact, the self-induction becomes complex, with, so the real part is still positive, but there is now a negative imaginary part, and this is due to a critical layer inside the vortex, which occurs at the radius where the angular velocity of the vortex is equal to the Bruns-Weisler frequency. And so this critical layer damps the bending deformation. So this is why we have a negative, an imaginary, a complex self-induction. And it's this. The red is a prediction from this formula, and the black line is the exact result obtained from a numerical numerical integration. And so when the Froude number is increased further, here therefore Froude number equal to 2, so now the real part of the self-induction becomes negative, like in homogeneous fluids. But the threshold for which the self-induction, the sign of the self-induction is reversed, depends on the Rossby number. So this was the first effect. The second effect is a strain effect here, and this is simply the effect of the companion vortex on the perturbation of this vortex. So, for example, here in this cross section, when you the red vortex move closer to the blue vortex, and so it will be advected faster. And so this is described by these terms. And finally, we have the opposite effect, which is the effect of the perturbation of the second vortex on the basic flow, the first vortex. And this is called a mutual induction effect. And so this depends on mutual induction function, psi and chi here, which describe how the perturbation outside the vortex decays. And this function are also different in stratified and rotating fluid than in homogeneous fluid. So in stratified and rotating fluids, that depends on the K, the wave number, B, the separation distance, and the ratio between the Froude number and the Rossby number. Okay, so now we have seen the three effects. So I just would like to recall the condition of validity of this equation. So they are valid when the ratio between the separation distance and the vortex radius is large. The wave number has to be large when to be small when rescaled by the vortex radius and the Froude number. They are valid whatever the Rossby number, and in this range of Froude number. So, but this range is quite large because here the parameter b over r square is large. So, with this equation, we have been able to predict the zigzag instability of vortex pairs. And now let's look at the case of a von Karman street. So two infinite rows of counter-rotating vortices. So the spacing ratio is the ratio between the distance between the two rows, and b is the distance between the vortices in a row. And so the stability of this has been investigated by Karman in 2 dimensions, and in 3 dimensions in homogeneous fluid by Robinson and Safman. So now let's look at its stability in a stratified and rotating fluid. So this is, for example, the equation for the displacement perturbation of this vortex in this direction. And so these equations are quite complicated because you have to take into account all the effects of all the vortices, so all the strain and mutual induction effect of each vortex. So here we have, for example, the first line is the self-induction of the self-induction. Here the second line is the strain and the mutual induction of all the vortices of the first line. And here we have the strain and the mutual induction of the vortices of the second vortex line. And so we have the same equation in the y component and two equations for each vortex. But here we are going to look at perturbation of this form with with a growth rate sigma and with the parameter phi here, which describes the periodicity of the perturbation in the rho wise direction. And so here I'm going to show you only the most unstable mode for over all value of phi.
Why there is no screening effect with the deformation radius? Why do you need to take into account all ones?
Yeah, we could stop at some point, yes. There is a screening effect. But because you have sums and they converge to a finite value. So in fact, this is the first result for a strongly stratified fluid with a fluid number equal to 0.1 and without planetary rotation. And there are two different cases depending on the spacing ratio. When it is lower than 0.4 and higher than 0.4. And in this case, this is a growth rate as a function of the vertical wave number. And so in this case, we see that the growth rate increase and then reach a maximum. So in this case, we have a three-dimensional instability. The most unstable instability is three-dimensional. While when the rows are distant, the maximum growth rate is obtained for zero wave number and then decreases. So in this case, the dominant instability is two-dimensional. And here are the eigenmode corresponding to this instability. So here in the first case, the vortices are bent like that. So if we do a cross-section here in this horizontal plane, what we see is that all the vortices of a given row are displaced in the same direction, and the vortices of the other row are displaced in the opposite direction. And so, and if we were doing a cross-section just above, we will see that the motion will be reversed, and so there will be the two rows will come closer. And so this instability induces vertical modulation of the spacing between the two rows. And so it's a bending instability, and so we call it zigzag instability. And while in the case of distant rows, it's a two-dimensional instability, and in this case the vortices are not displaced in the same direction for a given row. So, for example, here this vortex is displaced in this direction, this one in this direction. So the two vortices come closer, and so this is a two-dimensional pairing instability. Now let's look at the effect of the stratification. So when we vary the fluid number from 0 to 1, there is no much change. So the maximum growth rate remains the same, but the wave number change a little, but this not very much. So this shows that the maximum growth rate is proportional to the strain, because here it has been scaled by the strain, and here and so this shows that the most amplified wavelength scale as a fluid number times b, the separation between the vortices, since here the wave number is scaled by bfh. And when we further increase the fluid number for 1.2, there is an abrupt decrease of the growth rate, and so this is due to the critical layer which occurs inside the vortex as soon as the fluid number is larger than 1. And in the case of distant rows, the pairing instability remains dominant because it's a two-dimensional instability. Now, if we vary now if we look at the effect of the planetary rotation, so we fix the fluid number, and so we see that the zigzag instability remains dominant for all Rossby number. So its growth rate decreases with the Rossby number, but then for small Rossby number, the growth rate remains constant, and the the most amplified wave number decreases with the Rossby number, and for small Rossby number it becomes, so the most unstable wavelength becomes inversely proportional to the Rossby numbers. So this is what we expect from the quasi-geostrophic theory. And again, when the spacing ratio is large, the pairing instability remains dominant. So now there is an important question: is this theory valid? And so to check that, we have done a numerical stability analysis of with a pseudo-spectral code linearized around the basic state. So we start the simulation from a white noise, and then for large terms, the perturbation consists only in the most unstable mode. And so here I recall you the result for in the case of closed roll. So this is the effect of the Froude number for a given Rossby number, and this is the effect of the Froude number, the Rossby number for a given Froude number. And here are the numerical results. So these are the symbols, and so we see that the agreement is quite good. There is a difference at large wave numbers. This is because of the long wavelength assumption in the theory. But the argument is good, and even here it's excellent. And I would like to stress that there is no fitting parameter at all in the theory. And so this shows also that the zigzag instability in this range is the most unstable instability. There could be other type of instability like centrifugal instability or elliptic instability. But here, the zigzag instability is more unstable than this instability. So we have not done any simulation or experiment of this instability, but there might be an experimental observation of this instability from the experiment of Pro, Fincham, and Someria, where they were towing vertical cylinders. And here we see the wake behind a cylinder. So this has been obtained from three-dimensional PIV measurements. And we see that the vortices are bent, and this looks like to the mode we predict from the theory. How much? 2 minutes. So I was planning to explain you the physical mechanism, but I will skip that. So we have also looked at the stability of the symmetric double row. So in this case, the most unstable instability is always three-dimensional. It is always the zigzag instability. And so to conclude, we have developed a theory of the zigzag instability in a stratified and rotating fluid, and this theory can be seen as equivalent to the vortex filament methods in homogeneous fluids. And this has shown that the von Karman street is unstable to the zigzag instability when the spacing ratio is below 0.4, and this occurs when the full number is typically below 1.5, and this is independent of the Rossby number. And when the rows are distant, the dominant instability is the pairing instability, and the double symmetric row is also unstable to the zigzag instability. And so this shows that the zigzag instability in most cases is generic and dominant. And to prove you this further, here are some simulation of a random distribution of vortices. So we have 10 vortices, 5 positive and 5 negative. And so let's start the simulation. So the fluid is stratified but not rotating. So at the beginning, the vortices evolve like point vortices. But soon, now we start to see bending deformation. And this deformation breaks the vortices. And at the end, you have some pancake vortices. So, thank you.
Time for questions.
In a maybe some of the other simulators can comment on this too. But in a simulation like that, have you done anything to identify the direction of energy transfer and the strength of energy transfer. Presumably it's going to small scales, but we don't know how fast.
Yes, we have not looked at that. This is only a preliminary simulation, but we plan to do it.
You showed this picture of the vortex street generated by an island. Does the theory predict this meteorological observation?
I don't know. We will have to look at the food number, and because the food number has to be lower than unity, and so I don't know if in this case the food number is in this range.
In the case of island, the food number is clearly lower than unity. But it's very shallow systems, or this is a question how it applies to shallow system, like in geophysical situation. There's a limitation for the vertical scale.
Yes, here to simplify the problem, we assume a uniform flow along the vertical, but in the case of shallow flow, you have effect of the boundaries, and so if the height of the fluid is smaller than the wavelength, then I think that the vortices will remain two-dimensional.
Any other questions?